Where are we going?
We are going to Steel Structures Laboratory.
Okay, Steel Structures Laboratory. What's going on in there?
We do some experiments there, so we try to break things in
You're
two
breaking
parts.
things in the laboratory, cool.
Yes.
Is it for fun?
It's also for fun, but we also try to understand and validate our models, how they can be validated by experimental research.
Okay, so you're interested in how long different steel things survive?
Yes, we try to understand what is the failure mechanisms, how much load they can sustain, and in such way we have different models for predicting, for example, the service life, but we try to understand how they really works, and the experimental work is needed for that.
Okay, and where is it needed?
Everywhere. Steel structures you can find everywhere. So
Like for example,
you have cranes, railways, working machinery, bridges,
cars,
everything. Your car is made of steel also.
Okay, and even a bicycle.
Yes, even a bicycle.
Okay, so we are now inside the laboratory.
Yes, so this is the place where we break things.
Okay, and this is what is happening in here right now.
Yes, we are running a fatigue test, so we put some cyclic loading on the welded sample.
Okay, and the sample you're saying is this detail?
Yes, so in most of the cases we investigate things that we put some smaller specimen than the real structure, but these small things that is now the welded connection is a part of bigger structure, and in such way we can investigate the critical components of structures. What are the most important joint and connections in the structure that are the most critical in terms of failing.
And here you're saying welded, it's this thing in between two parts,
yes,
right?
So
it's kind of glued together.
It represents a connection that is welded with the molten material, which is called weld in this case.
Okay, and it's, I suppose, the weakest place of the whole thing.
Yes, it's usually in welded connections the fatigue is a big issue.
Okay, and this moves up and down, so it applies some stress to it? Or?
Yes, so we have a cyclic loading. We have a cylinder that moves up and down, and the force at the moment is approximately 40 tons, so 40,000 kilograms, so it's quite much.
Okay, a lot of elephants need to sit on this one.
Yes.
And the force is applied like constantly on and off, and it's not just once and the thing is broken, it's constantly. Okay.
So it runs between maximum and minimum force, and eventually we find that we can have some crack in the specimen and it fails totally.
Okay, and here we also have the computer that shows us what's going on.
So here we can see the cycles going
what
up and
cycle?
Down. Cycle is one repetition from up and down.
Okay, and so it's kind of approximately once a second?
Yes, 0.9 hertz is at the moment is the frequency.
So almost once a second?
Yes.
Yeah.
So it runs approximately 75,000 cycles a day.
Okay. And how much until this thing is broken?
For this sample it's few days, so it takes like 1 week approximately in this case to break it apart.
Okay, and is this thing running constantly, or do you switch it off and you go home?
It runs all the time, so it doesn't have any working hours, so it's our machine to run all the weekends, all the days, all the nights, so it's running constantly.
You're really obsessed with breaking things here.
Yes, this is the thing.
Okay. Can you show me how the cracked things look?
Yes, sure. Let's have a look.
Let's go. Okay, you found something that got broken.
Yes, so this is something that we have already done. So this is the same specimen that we saw previously, and it has fallen apart.
Okay. And how it was together like both parts? Yeah.
Yes, so they were like this, and after a time, after the cyclic loading, it has fallen apart. So first we have had some cracking. It's called fatigue crack, so it has grown like a semi-elliptic shape, and eventually the whole specimen has failed in two parts.
Okay, and this part is welded, right?
Yes, so we can see the weld.
The weakness.
Yes, we can see the weld.
Yeah.
And usually the critical part of these kind of connections is the transition from the plate to the weld, where we have like sharp transition, and the failure origins from there.
Okay, And so in your work, you are building mathematical models to predict when and where they crack.
Yes, so if we look at this from the engineering viewpoint, they cannot do such experiments for all the components that is designed. Yes.
Yeah.
So to do that, to eventually understand what is the life or service life of this kind of component, we need to have some models.
Okay.
And we have various models for that, but to understand, do these models really work? So we need to have some experiments.
Okay. Clear. Let's have a look inside the model.
Okay.
So here is the model, or it is the description of that model.
Yes.
What does it do?
Okay, so besides that having just the applied load, what was the 40 tons in the test,
Yeah.
so we need something more to understand the failure. And the conventional way to do it is to have just some statistical model to understand the scatter in the results. But we have developed our own model to understand what happens in the material, how the failure actually.
Okay. Does it work better than statistical models?
Yes, we try to
Excellent.
improve our accuracy.
Very good. Okay. And what does it take into account, your model?
Yes, instead of just having the applied stress in the model, so we do consider multiple different parameters. So we consider the material strength, so we have different steel grades.
And that makes sense. If steel is stronger, then it's not that fast to break.
Actually, it can be vice versa, but still
How come?
the fatigue is an issue that you don't actually get some benefit from the strength itself necessarily.
Okay. So it's not linear. You cannot really.
Yes.
Okay.
But anyhow, it is an important factor that we consider the material strength. And then we have the residual stresses. So we have put some molten material in the joint or the connection, and it shrinks and it causes residual stresses component.
Well, wait. So is it when you weld things together?
Yes.
Then there is kind of, let's say, this glue.
Yes.
It's warm, and then it gets cooled down,
Yes.
and it shrinks,
Yes.
and so it kind of pulls together the parts,
Yes.
which cannot actually get pulled because they are part of a bigger structure,
Yes.
and so that causes some extra stress inside,
Yes.
which is called residual stress.
Yes. It's an internal stress that is self-balanced in
Okay.
the component.
It's very similar to actually just human stress, like something is just not resolved inside.
Yes.
Okay.
Okay. Then we have also the applied stress ratio. So what kind of loading we have. In the laboratory test, we went from 0 to the maximum
There was this.
cyclic loading.
Yeah.
But
So
we
it's
have
practically, we have seen that sine wave, and
Yes.
it's practically the difference between the up and down.
yes.
Okay.
So that's the stress range, but it can be in the different levels. So we
Yeah.
can in the other part it can be in the compression side, and it can be in a fully tension. So it
But this one should be straightforward. So the more the stress ratio, the faster thing breaks.
yes, basically
Okay.
in most of the cases.
At least something is clear.
Yes.
Okay.
And so to account for those components, we have developed our own model, which is called 4R method, and we have 4 parameters included in the analysis.
And they are that stress
Material strength,
material strength,
residual stresses, applied stress ratio, and weld toe radius.
weld toe radius,
Yes. So it describes the weld quality. What is the
Okay.
quality of the weld?
or how much glue we put in there.
Not exactly, but it depends the shape of the glue or the weld.
Okay, the shape of the glue. Will engineers hate me for using the glue metaphor for welding?
Yes, certainly.
Uh-oh. Sorry,
You're
guys.
in trouble.
Okay, but then everybody else would understand what we're talking about.
Yes.
So. That's worse the trouble. What is the output in your model? You're trying to understand how fast things break. Right?
So yes, we have a correlation between the applied stress and the time or the number of cycles until the failure.
Okay. Okay, and applied stress is the output of the model.
Yes, so as a result we get the corrected value of the stress
Okay.
based on
And
these four
okay.
parameters.
And is it the higher the worse?
Yes, the higher the load is, usually we have a lower number of cycles. So that's
Okay.
the basic thing.
So we would wanna target the lowest values.
Yes,
of
and
this.
we have different means to get it lower.
I've heard from many engineers that they would do one factor at a time analysis.
Yes.
So, for example, they would change one factor while others are fixed, and this way they would understand how the model behaves and how the output can be actually shaped into what they want. Is it a good idea to do it, or?
Yes, it helps you to understand how single variable affects on the results. But the tricky part is, for example, in our model, is that the effect of individual parameter is different in different cases. So by just changing the one parameter in one case doesn't provide you a proper solution or proper answer. What is the influence of
Okay,
single?
because if another parameter is in a different case, then this parameter might be having different effect.
Yes, that's the thing.
Wow. Okay.
That makes things complicated.
Okay, and you probably try to do some sensitivity analysis,
Yes,
right?
we have tried it.
Okay, so that's sensitivity analysis.
Yes, so
that you already made.
So we previously did an analysis where we changed each parameter one at a time to understand what is the effect of parameter on the output.
Yes, but correct me if I'm wrong. Usually when I see an analysis like that, we can see just one graph. You have here, what, 3 by 4?
Yes, so
12.
to understand the different cases, so each parameter has different effect on the result in different case. So we have categorized these cases, and then we have changed inside that case, we have changed the parameters.
So you are trying here to combine kind of scenario analysis and one factor at a time analysis to achieve some kind of multi-factor analysis.
Yes.
Okay.
To understand to have at least some overview on the how individual parameters affect on the result.
But I would say it's quite difficult to read those 12 graphs.
Yes, certainly. This is good for a person that really understands what is the model.
Like you.
Yes, like me.
And nobody else in the world.
Maybe someone, yes, still understand, but it's for some person that is really in the model, understand the concept, but for a person who is not familiar with the 4R method, maybe doesn't understand anything from this figure.
Yeah. Okay, and that must be why when I wrote you about SimDec and this experimental approach to sensitivity analysis, you were actually very interested to try.
Yes, it's worth trying to understand this and have a more clear picture what is the effect of each parameter.
So you already know everything clearly from here, but you just wanted to have a communication tool for it. Yes, here it is. You just sent me the data, and I ran it through the algorithms, and this is what we got.
Yes.
Okay, and we had there these 4 factors that you mentioned, 4 input factors, and this outcome factor, that the representation of stress. And what happened next, I was actually amazed with the graph and the kind of nonlinearities that are going inside.
So that's the tricky part of 4R method.
Yes, but it's also I don't know, it's beautiful to be able to observe the model like that. So can I try to describe what's going on inside your engineering model?
Yes.
Okay, so we have 2 factors here that are the most important. First factor that accounts for more than half of the variance in the output is the residual stress.
Yes.
That thing that creates the inner tension when things are welded together. Okay, and the next one is the R, which is
applied stress ratio.
Applied stress ratio, the difference between the peaks of the pulling and pushing.
At what level is the applied stress?
Yep, and what we can see here is that first the residual stress divides the whole thing into 3 distinct scenarios. One is blue, which is spread all over the place, so meaning that we cannot really affect the result by changing it in that scenario. But then the yellow and the green ones are very compact, and they represent different levels of the resulting stress. So we can say that we definitely don't want, and the bigger the outcome, the worse, right?
Yes.
So we definitely don't want to go to the green one with the high values of stress. We might consider going into yellow because it kind of focuses us on the middle values of stress. And we might be willing to go into the blue, but well, it can be as low and as high, we cannot really do anything about it. Okay, but then we have the stress ratio. And here something interesting going on. So when the residual stress is either yellow or green, forgive me my vocabulary, then the stress ratio actually doesn't affect much.
Yes,
So
that's
again,
the thing.
Yeah, so residual stress, when it's high or medium, stress ratio doesn't matter.
Yes.
But when residual stress is low, so there is low tension in between them, right?
Yes, or it can be even in compression.
Okay, or it can even be in compression. Okay, that makes sense. Then the applied stress ratio makes a lot of difference, and if we keep it low, then we really get very nice values of the resulting stress, and so the duration of the service of the structure. Okay.
Sure. So I can grant you a master degree in fatigue.
Thank you. Thank you. So it's just the magic of SimDec just made me an engineer.
Yes.
Okay. What do you think? Would it be easy to use this to communicate the main point of your model?
Yes. With this figure, I think we can improve our dissemination, so we can explain things a bit clearer, more clear version of the how things or different parameters affect the results.
Okay. You mentioned that your model is quite nonlinear, which we can clearly see, and well, we've got some interesting results for your model that is able to explain it. But now, what do you think? Would it be useful for some other engineering models?
I strongly believe on that.
So they're all nonlinear, pretty much. Something weird going on. Okay.
So there's high potential to explain and disseminate and show different things on different kind of models.
We checked your academic model, right? But there is also a whole real world out there with structural reliability problems, and there's a huge amount of choices probably engineers should make. What kind of choices are there? What kind of decisions are required?
So of course, before going into our model, so you have to know what are the critical components of the structure. So you need to analyze the whole structure and screen which are the most critical parts and from which location the structure will fail if it fails.
True. And then, so there is a design of the structure that is important, right?
Yes.
Then the material of the structure that is important. The operational conditions are important because they also create different types of stress on the structure. So we can easily say that structural engineers, face huge amount of problems with huge amount of different factors that contribute. They're probably effects of them are nonlinear, and there are some weird interactions that are not necessarily intuitive. And in all those problems, SimDec would be valuable.
Yes.
Okay.
I'm sure.
Okay. What did you like personally about SimDec?
I like the visualization. I'm a person that really tries to go beyond the academia. So I believe that with the SimDec you can really disseminate your results in a such way that everyone understands what is the outcome or what is the relation between inputs and outputs. Because even with you have a very good scientific model, you really need to kind of highlight what is the importance.
Yeah, tell the world about it.
Yes.
Yes, it was actually my original idea was to make myself understand what was going on inside a model I was working in. And it's cool that I'm able to do the same job for somebody else, especially so different from myself.
Yes, certainly.
Yeah. Okay, Antti, thank you so much for this talk. I enjoyed it a lot.
Thank you very much.